So now I'd like to introduce Claire O'Connor, who was awarded a SURE fellowship, what is it? Summer Undergraduate Research Experience for the summer, which allowed her to work on a research project here at SUNY New Paltz. She's going to talk about working with data from the LIGO detectors for cosmic gravitational waves. And she investigated something to do with cosmic strings. Let's see, can we distinguish between cosmic string cusps and colliding black holes? And I'll let her tell you more about her work. That's good.
All right, so my name is Claire O'Connor, and I did work on distinguishing between cosmic string cusps and colliding black holes using gravitational wave data. So to start out, let's talk about something that is a little more familiar to us. So electromagnetic waves, aka light, those come from an oscillating electromagnetic field, and they're produced by accelerating charges. This is what we're used to observing the universe with. We're used to looking at light from anything from luminosity, of course, to the mass of something and figuring out orbits. We look at light for a lot, pretty much everything up till a few years ago. Analogous to that is gravitational waves. So this, instead of being an oscillating electromagnetic field, we're dealing with an oscillating gravitational field. And these are produced by accelerating masses. And you can see over here, I have a couple stars for electromagnetic. And then on the right, we have those two very dense masses spiraling in towards one another. And we'll get to what's going on there in a moment. So starting out with our cosmic string side of things, cosmic strings, they're very long, very dense, very thin. And they formed as the universe condensed. They're called a type of topological defect. So on the left, we have a glass of ice with very cloudy ice in it, and then we have very clear ice on the right. And the reason why we can't see through the ice on the left is because there's defects in there. There's impurities. And cosmic strings are kind of like an impurity, but for the universe. These cosmological strings, cosmic strings, they interact with other strings in a very interesting way, and we call that intercommutation. So intercommutation, it kind of looks like this. So we have a red string and we have a green string, and they're overlapping here. And at the point where they overlap, they make contact, they interact, they sort of break, and you get these discontinuities, these sharp edges. And one type of discontinuity you can get is a cosmic string cusp. And these cusps release a lot of energy, and they do that in the form of gravitational waves. If you think of cracking a whip, when you crack a whip, you get a really loud sound. It's a very rapid release of energy in the form of sound energy. Similar to this, we have the cosmic string cusps, which are rapid release of energy, but it's in the form of gravitational waves. These have yet to be detected, but scientists, to an extent, are still looking. But what we're really focused on right now is compact binary coalescences. Compact binary coalescences are pretty much exactly what they sound like. So very dense bodies, there's two of them, and they orbit each other. And over time, they lose energy in the form of gravitational waves. And when they lose enough energy, they coalesce, they combine, and they actually merge. And when they merge, there's, once again, a huge release of energy in the form of gravitational waves. These have been detected, and the anniversary actually was not too long ago. September 14th, 2014 was the first time we detected gravitational waves, and it was a CBC, and they have been CBCs ever since. Just to give you an idea of the parts in a compact binary coalescence, we start out with the in spiral. So the in spiral is when they are, as it sounds like, they're spiraling in towards one another. Once they get close enough, we get a merger, and this is when they actually collide and they're forming one mass. And after that, we get something called a ring down. And that's when it's sort of settling into that nice uniform shape. Keep in mind that for this research, we focused on the in spiral part. So the models we used in order to actually go ahead and find these gravitational waves, it only had the in spiral included with it. We did not include the ring down. And fun fact, it's called a ring down because it's like a bell ringing down. Just because they all kind of correlate with their names, but that one can be a little bit funny. So we focused on the in spiral. And as far as actually detecting them, we have something that works very well in our favor. So gravitational waves distort space-time, and they do it in a way where it's not the same in every direction. So if you look at the left one, you can see, or even on the right too, it's getting squashed down and it's elongating again, but it's being squashed on the side and it repeats. And just to give some context, so the one on the left, you can kind of see depth to it. You can kind of see what's happening throughout the whole thing as this gravitational wave propagates. But the one on the right is just a face on. It's basically the very edge. Something that might be hard to see is that the depth is not affected by this gravitational wave. It's only the plane that we're looking at. So because that works, we're able to actually go ahead and detect them. And we use that using something called a Michelson-Fabry-Perot interferometer. This is what LIGO is. So the Michelson interferometer part, you have light come in from the left, it hits a beam splitter, it goes out and hits two mirrors, each of those split beams, comes back, recombines, and goes into the detector. And the reason it's really nice that these gravitational waves distort space-time differently is because if the distance from the beam splitter to mirror one, or the distance from beam splitter to mirror two changes, we will get an interference pattern and we will detect that in the detector. We also improve this by adding a Fabry-Perot interferometer into each of those arms between the beam splitter and the mirror. And that just increases the effective length. So if you think about a 2x4, if it's a foot long and it's warped, you're not really going to see it. But if it's 8 feet long, you're going to see that difference a lot better. So this is how we actually detect them. We use an interferometer, and we're lucky because they don't distort everything the same way. An example of what that might look like, oh, excuse me. Yes, it'll result in interference, and something like LIGO, the Laser Interferometer Gravitational Wave Observatory, will actually detect these. There are more observatories out there, but LIGO provided the data for this project. This is an example of what that data might look like. And as you can see, you can't tell what's in there. It's basically impossible to look at this and see, I know there's a CBC in there. It's impossible. So we have to use something called a template. And a template is essentially a good guess. So we take a guess as to what we think this wave is going to look like, and we match it to the detected data. So for example, I have my blue pentagon, which is my data. I have my green outline, which is my template, and I'm going to match them. And I see these don't really match up that well. But if I rotate it a little bit, still doesn't match. Rotate it more. If I keep rotating it and checking how well they match, I check the correlation, we can actually see eventually they match very well. And I know that because there's a good correlation, that my data looks like my template. There are different shapes for different types of sources. We have a cosmic string template is going to look different, presumably, from a CBC template. So we make different templates for everything. This is what our cusp template looks like and our in-spiral template, and that's associated with our CBC, our compact binary coalescence. And looking at this, they look the same, or at least very, very similar. And you might think, okay, well, maybe we can look at it another way. So we took it and we did something called a Fourier transform. And all that is we took our data from the time domain and we put it into the frequency domain. And that's what this looks like. So we put it in the frequency domain and we can still see they look very, very similar. It's still very hard to tell it apart. But I know what you're saying. You just want to see the math. Who wouldn't? All right, well, here you go. Oh, they're different. There's a plot twist. Templates have an inherent quality called loudness. And this relates to the amplitude of the template. Templates with different amplitudes are going to interfere with results. Normalizing this is going to mitigate the problem. So what we do is we basically choose, I want it to be this amplitude, I want it to have this maximum, and we do some math to make that happen. So what I'm going to do is I'm going to take some pieces out of the equation that don't relate to the shape. So first, I'm going to take out this because that's anything above our F max. We cut it off at our F max. We didn't want to deal with it and makes it hard for normalization. Now I'm taking out everything that doesn't have to do with shape. If you were paying attention closely, you'll notice that some things disappeared. And we're left with these. So you're left with f to the -4/3 and f to the -7/6. So we have -8/6 and -7/6. And those are remarkably similar. So moving on, just to give you, again, to show you that, hey, these have the same maximum. And there is our term. And that is what the shape is based on. And moving on, this raised a peculiar question. We noticed that they looked very, very similar. And my predecessor, Aidan Brophy, also worked with Dr. Myers, had compared a cusp template and an in-spiral template to 4 events. And one of them came back like this. In orange, we have the cusp template, and in blue, we have the in-spiral template. And the cusp template won. But LIGO has flagged every single thing as a CBC. So this got us thinking, is it possible that this is a fluke, or is this repeatable? Can we find this somewhere else? So we looked. Okay. So I apologize, it looks like there's an issue with the formatting, but you can get the idea with the diagram on the right. So on the right, this was tested on CBC events. And the CBC events, we took a cusp template and we took an in-spiral template. And we tested them both on a CBC event, and we took back the SNR, which is basically how good of a match it is. Then we got our SNR back, we put it in distribution, and this is an idea of what that raw distribution looks like. On the left, it would have been the same, but it would have been for cusp injections. And an injection is a sort of simulated signal. We have not detected cusps, but we do have injections of it. And those simulated signals just test the ability to actually get that signal back. It's a test for LIGO. So we are able to test our templates on those, just not actual events. Brilliant. Okay. This is the more important part. Whenever an SNR came back higher, we made note of it, we got the difference, and we put it in a histogram. We put it in a distribution. We did the same thing, and we got the percentages as well. We did this for the cusp injections and the CBC events. And every time one of them was higher, it went in the histogram. And you'll see, once again, similar distribution between the cusp and the CBC. But if you look closely, none of these say that the in-spiral came back higher. All of these, this entire distribution, every single one came back higher as a cusp. So that might make you think, oh my gosh, LIGO made a mistake? Well, no, because they've looked at this. And we have a paper from LIGO where they actually went in and did the same thing I did, but they did it, you know, with 1,043 people. So it's either that 1,043 people are wrong, or it could be an artifact of the coding. But regardless, you can even see here is the reporting on what they did. They're saying that they looked to make sure that everything were, they were CBCs. They looked for cosmic string loops again, and they didn't find any evidence. Regardless of what the results mean, or why they were incorrect, or why some of them might be right, it's still an interesting mystery, and I'm looking forward to whatever they find next. So with that, I'd like to thank New Paltz for funding this research. I'd like to thank Dr. Eric Myers for helping me through this, and everyone else who helped me to put this presentation together.
Do you have any questions?
What is a cosmic string?
What is a cosmic string?
I haven't really heard of that before. I mean, I've heard of string theory. That's.
So if we go back to, there we go. So cosmic strings are very long, very dense, very thin, and they really are just an impurity. Like, that's the best analogy for it, at least as of I know right now.
String of what?
Matter just like anything else.
What scale are we talking?
So the thickness of them, subatomic, very, very, very thin. But the length of them, cosmic scale. They're gigantic, but they're incredibly thin.
And this is theoretical, or we know they exist?
I mean, at the moment, they're theoretical.
And they're formed in the Big Bang?
Shortly after the Big Bang, as everything's cooling and condensing.
So so you weren't able to find the data relating to the strings from LIGO. So is that a limitation of our instrument? And does that mean that once we get the spaceborne gravitational detector, which will be a much larger scale, is that possibly going to be where we're going to find the data?
I mean, it's entirely possible, because the one going out to space, when they did that test run, it was remarkably sensitive. So it's possible that we could detect a cosmic string cusp, you know, the gravitational waves as a result of that. You know, I can never say for sure, but it's definitely more likely to happen out in space than on Earth, where you have, you know, earthquakes and any sort of vibration, really.
Spark.
If oh, okay. Okay, cool. Happen is it like what kind of gravitational effects or other effects would they have?
Based on how dense they are, I can't speak to exactly what would happen, but they are very dense. I could imagine you might feel a pull. I can tell you that if you touch one, you would cut yourself because of how thin they are. But as far as the magnitude of the gravitational pull, I'm not quite sure. But because they're so dense, I would imagine there would at least be something detectable.
Okay. Some more friendly fire.
Did this at my last presentation too.
So, just going back to the math side of things, all that math that you got rid of, that's all because when you normalize it, right? You're just looking at the shape of it.
Exactly. So
But all that math, that's just referring to the magnitude then? Is that why?
everything that disappeared just had to do with amplitude.
Amplitude, sorry. Yeah,
Yes.
that's what I'm, right, yeah, it's constant, so you just get rid of it. Okay, thank you.
Yep.
Any other?
What do you think? What's your leading idea about why there's a difference between LIGO and your results?
I think it's an issue with my code, to be quite honest with you. Haven't found one yet. But that would be the leading cause. There are other reasons that could easily contribute to it. So for example, I was talking about how I'm only using the in-spiral part. But there's a whole ring down that is also associated with CBCs. So it's possible that not having that ring down, they could have very similar beginnings to the gravitational waves, but that ring down could have an effect on our ability to detect it. There's also, I'm using primitive templates. So I'm using what was available to me. So these are older. It's not, the ones LIGO used are much more detailed.
May I ask you how long it takes to compute one of those?
Computing, if I were to do an entire file, which I think is about 800, 900 lines, it would 12 hours.
Whoa,
For this, I computed about 50.
cool. That's awesome.
I'm going to ask a leading question, just to recap, okay?
Okay.
Aidan Brophy started working on this, and he looked at 4 events, and one of them showed that the signal indicating that it's a cusp was stronger than for an in-spiral. The other 3 then were in-spirals.
Correct.
You've looked at about 50 of these, and how many of them did the in-spiral appear stronger?
For this one, I tested, I believe
50,
it was 48 for
48?
this.
Okay. And they were all stronger. They appeared to be a cusp stronger than to be an in-spiral.
Every single one.
Okay. So that's now the mystery has been turned around. First it was, oh, one of these looks like it might be a cosmic string. What's up with that? And now it's all of them look like cosmic strings. What's up with that?
Exactly. But it's still interesting because,
Oh,
okay,
yeah.
now we have to look at the ring down. Now we have to see if we can find a better template. So it still leads to some interesting questions. And I'm very excited to, go and pursue those and see if I can actually.
Or you've discovered that everything's cosmic strings, but
Or I'm going to get a Nobel Prize. It's one of the two.
don't hold your breath. But it's still really interesting. So, okay, well, let's thank Claire.